I'm going to introduce you to the data that Magellan sent us and that allows us to study the surface. As Lucia explains in her talk, Venus is covered by clouds. That makes it difficult to study the surface, but fortunately we have technologies like radar that allow us to peer into the clouds of Venus and other planets. For those of you interested, for example, in the geology of Titan, Titan is also completely covered by clouds, so it's also necessary to have radar images to study the surface. So this technology allows us to see the surface, but it's not like the normal images that you could be used to see. Why? Because we are using a different part of the electromagnetic spectrum. This kind of sensors, instead of receiving the light that is reflected by the surface, they carry their own energy. They is what they are called active sensors. They emit the energy and measures the return of the surface to the sensor. So in this case, we work in these frequencies. The SAR band, the synthetic aperture radar bands, are between these, in this part of the electromagnetic spectrum, and this is what allows us to pass through the clouds and to obtain a return from the surface. As Lucia said, all these images were obtained by the Magellan mission, the NASA, that was around Venus for 4 years. It was a relatively simple and low-cost mission for the time, but whose results were amazing and still are being used today. The Magellan probe carries the radar. The main instrument was the synthetic aperture radar, but also carries an altimeter and a radiometer that provides with other data sets that we are also going to see. What you see here is how these active sensors work. The probe emits the pulse of energy and then measures the return, and with that information is how it produces the images. One important thing to consider when you are interpreting these radar images, and it's something that is going to be present in the heads-on later, and we are going to repeat this in several times because it's very, very important for you to understand what you are seeing in the surface, is that these radar sensors, they move in the orbit, and they illuminate laterally the surface, and they measure the return. This lateral component is very, very important because the geometry of the image is really conditions by the geometry if you are looking from the right or you are looking from the left. These are examples of all the data sets that were returned by the different science cycles of the Magellan mission. There are several cycles. This first cycle, the cycle 1, produced images of about 98% of the surface of Venus. In this case, the illumination was from the left, and we are going to see that in detail later. Then in another cycle, the cycle 2, produced images that were in this case illuminated from the right. As you can see, the coverage of the planet was much less in this case. And a third cycle make also images of some parts of the surface imaging from the left, and allow to have some part of the planet with a stereo global data coverage. We are going to explore these data sets later in the hands-ons in detail for you to see the images and how you can see the different geologic structures and terrains with these different geometries. The other data that Magellan provide was a topography. It was not the best topography that you can find in the solar system, and we are going to see that this is a problem to understand the geology of some regions, and also other ancillary data like global microwave visivity, reflectivity, and slopes. So what you are seeing at radar image. If you remember from the previous talk, all the images from the surface of Venus are in black and white, in tones of gray. And what that means is that you are seeing not really an image of the surface, but you are seeing the texture of the surface. All these different shades of gray, all these lineaments are structures and materials, but very conditioned by the geometry of how radar works. The radar image is going to depend on many factors. For example, the electric constants of the terrain that in the Earth is very, very influenced by the content in water. In Venus, we don't have that problem, but for you to know, for example, we use radar images on the Earth to measure soil moisture from orbit. The other factors that are going to be important to understand these images and to interpret them are the texture in terms of the roughness of the terrain. So what we see when we are looking at these images, we see things like this. The sensor emits the energy, and in function of how the texture of the surface is, you are going to have different returns, different structures and different tones of gray. For example, a smooth surface like this one is going to spectrally reflect most of the energy, and this is going to produce a low radar return. So the pixels of surface like this are going to be dark pixels. So when you see dark things in a radar image, what you are seeing is really smooth. It's a smooth surface. When the surface is more rough, you see that there is a preferent direction for the reflected wave, but there are scattering in many directions. In this case, the sensor receives more energy, the pixel is brighter, and you see different tones of gray that indicates that the texture of the surface is different. And when you have very rough surfaces, like for example the tessera terrains that Giulia mentioned, you have a very high radar return, and you see images with a very, very bright tone. So when you see a radar image, you are seeing different things that are depending on the texture. One thing that is important and that we are going to stress is that a texture is not necessarily means that a different texture is not necessarily means that we have a different unit or a different material. And we are going to see a very clear example of this. For example, on Earth, when you have a volcanic eruption, the flows that are close to the volcano, that are hotter and they have a high emission rate, they flow very well and they produce the so-called pajoejoe lavas that are very smooth and that in a radar image are going to be dark. But as the flow evolves and cools down, it's harder for the flow to run through the surface. It gets blocky. It gets rougher. It's more like an or a blocky lava flow. And in this case, this will be brighter in the radar image. But the unit is the same, are the lavas from the volcano. It's just a change in texture produced by the different evolution of the volcanic process. So you have to be very careful when you interpret a radar image, because the change in reflectivity, the change in the shades of gray that you see, not necessarily are going to mean that you have different units. And this is something that we are going to say in different times and that we are going to stress in the hands-on that we are going to have later. The other thing that is important to consider when you are interpreting the radar images is the topography. Because as we said later, before, the geometry of the image is very important. For example, if you have a left-looking image, you have the radar pulse from the left, the faces that are oriented towards the antenna are going to act as reflectors, and they are going to be brighter than those slopes that face in the opposite direction. So when you see these different variations in the tones of gray, from dark to bright in an image, you can also reconstruct the topography. In this case, you see that this part is going to be darker. You have the floor of the structure, and this other side is going to be brighter. If we have a different feature, a feature with a positive topography, is going to be opposite. In this case, we have this surface oriented towards the antenna, and it's going to be brighter. We have the upper part with medium values, and we have this part that is facing in the opposite direction of the radar beam, and it's going to appear dark. So when you have images that are illuminated from the left, like in the cycle 1 of Magellan, this is going to allow us to interpret the topography. But you have to be very careful, because if you have images of another cycle when illumination is from the right, this is going to be opposite. So it's very important for you to have clear if you are working in a left-looking illuminated image or in a right-looking illuminated image, because it's going to completely condition the way you interpret the images. So what we're going to do to map these images, what we're going to do in the exercise that we're going to do later. In the first step, we're going to identify structures that, as we're going to see now, they are easy to see in these images that real materials. We are going to map primary structures and secondary structures as a first step in the elaboration of our map. In the second step, we are going to start to map contacts based in the variation of the radar properties and in the interaction with the structures. What are the structures that we are going to map in the radar images? As Lucia showed us, there are many structures that are related to volcanic processes, but there are other structures like, for example, dunes or halos produced by impact craters that are also visible in radar images. We are going to see some examples here, but we are going to see a lot more of examples and how to interpret them in the afternoon session. For example, here you have examples of channels. These channels are going through the surface. You can see here how the channel is eroding a tessera terrain. So they are easily seen in these radar images. When we see channels that interact with other materials, for example, in this case, we can see here the channel and we see how the channel here disappears. We are going to use these contact relationships to establish local geologic relationships. For example, we can interpret here that these materials that are labeled like FCOA, that is the name of a unit that you are going to see later, are younger and post-date in this channel of here. We are also going to see structures like pit chains. You can see here an example of one of these pit chains that are interpreted like the surface manifestation of underlying dikes, volcanic dikes. If you remember some of the talks of the previous days, this could remind you of secondary craters, but on Venus we don't have secondary. I never seen examples of secondary craters because the thick atmospheres prevent this type of structures. We are going to see many volcanoes, as Lucia has said before, and for example, you see examples here of volcanoes. And all these images are illuminated from the left. For example, you see here how this circular structure, you see this part that is bright. That means that the slope is facing towards the antenna. So this is a positive feature. You can see the bright part here, the dark part here, and we see a small crater on the summit. So we are going to interpret this as a positive topography feature, a small mound with a crater on the upper part. We are going to interpret this as small volcano. We have the pancakes that Lucia mentioned. You can see here also how in this left-looking illuminated image, we see the surface towards the antenna very bright, and the surface that are opposite to the antenna that appear darker. We can see a scarp here, and you see how the brightness varies because of the angle with respect to the radar illumination. This part is brighter than this because of the orientation with respect to the antenna. So we have to play always with the geometry of how we are looking at the images to interpret the structures that we are seeing on the surface. We see many volcanic lava flows. We are going to see many examples of this. And we see also impact craters. We see an impact crater here, as you can see, is very bright in radar images because the ejecta is composed of blocks that are expelled in the process of the impact. So it's a very rough surface, and therefore it's going to be very bright. But you can see here a very interesting feature is that you see variations in the radar properties of the surface that are produced by the dust that is also formed in these volcanic processes, and that indicates that the impact is young. You still see the dust that is surrounding the area. This is going to make very difficult for us to map because in some parts they cover completely the structures. You barely see the structures under the dust, and they make modifications in the radar return of the surface. And you can see a very beautiful example of how the wind is blowing towards the northeast and produce these wind streaks in the volcanoes because of the presence of these small particle dust that are removed by the wind. The other structures that we are going to measure, to identify, are tectonic structures, and we can see some examples here. These are positive relief structures, what are called wrinkled ridges, and that are present in other planets and in the Moon, Mercury, Mars. If you have experience in previous planets, you are sure very familiar with these wrinkled ridges. You see how they are positive in topography. You have the remember always we are here. We are seeing left illuminated radar images. We see the bright surface here, and we see the dark surface in the part that is facing opposite to the antenna. So we interpret this as a positive topographic feature. We have some examples here of structures that are a little bit bigger that are interpreted as folds. In the case of fractures, the procedure is the same. You see some lineaments here, and if you see, for example, this structure of here, you see that you have a bright surface here, and a dark surface here. If we consider that we have the illumination from the left, we can interpret this as a negative topographic feature with a face that is oriented towards the antenna here, and another one that is oriented in the opposite direction here. And we interpret this as a graben structure, like the one that happens in extensional tectonic environments on the Earth. You see that there are many lineaments. There is not going to be a single radar image on Venus without tectonic features. And we see here how these fractures interact with wrinkled ridges. We are going to try to establish local temporal relationships between the different structures that we are looking in the radar images. And in this slide, you can see how texture also is important to understand and to interpret these radar images. This material of here, you see that has a different texture, is more reticular than this one of here. In this case, when we have these differences in texture, and we have structures or other features that allow us to establish local temporal relationships, we are pretty confident that this material is a different unit than this one of here. This is smooth, this is brighter, this is rougher, and we have the texture and the interaction with the fractures that allow us to really be confident and determine this at two different units at the time of mapping. The same happens here when you see very different radar returns. We have a very bright return here and a dark return here. If we see structures that crosscut some of the materials, but they are covered by the other ones, these are like two different lines of evidence for us to determine the possibility of a unit to be real. Because remember, not necessarily changes in reflectivity means that we are seeing the same different units. Another examples of clear contact relationships, we see here older material that is very fractured, and we see volcanic material that is partially covering these fractures. In this case, we are going to pretty confident determine that we have a geologic contact here. And in this case, we also have example of two materials with different texture. You see a very reticular texture here, a lava flow with a reticular texture, and another material when we don't see that texture, but as you can see here, these fractures disappear when you encounter this material. We are going to interpret this as a contact relationship because we interpret that this material is not just different in texture, but it's covering this material and the fractures that are deforming the previous unit. Just a final note, we are not going to use this today, not to make things more complicated, but you can see the radar images in both modes, in different modes. In the normal mode, that is the one that you have to the left, when all the principles that I have just told you, we can apply them. We have the differences in reflectivity related to the roughness of the surface, and we have the structures. But if you invert the image, and we are going to see how you can do that in QGIS later in the hands-on, what you do is you turn the structures from bright to dark. And from my previous experience, when you are doing structural maps and you are mapping structures on Venus, it's easier for our eyes to distinguish the structures when we see them as dark features in a more bright background, that when we see them as bright pictures in a darker background. We are going to play with this later in the hands-on. It has been a very quick introduction of how to interpret these images. Don't worry if things are a bit, like fuzzy now. We are going to stress all these principles of how to interpret these images later. You are going to have these presentations. These are some of basic references about how to study surfaces with radar remote sensors, and how to interpret these Magellan images to decipher the geology of the planet. And with this, I pass to Giulia, that is going to talk to you about spectroscopy on Venus.
So you have seen with Ivan how to map the geological structure present on the Venus surface. What we will see now is how do we map instead the mineralogical features on the Venus surface. Because mineralogy linked to the geological information is a key to understand the geological history, the activity, and the evolution of the planet. However, as already Ivan and Lucia told you, Venus has a really thick and dense atmosphere. And so unlike other planets of our solar system, like Mars or Mercury, for Venus, we cannot do hyperspectral imaging from orbit to study the Venus surface in the visible to thermal wavelengths. So the result is that most of the current knowledge that we have about the Venus surface is given from the radar data and from lander measurement, but we also have the VIRTIS data, and we will talk about that, and we will work on the VIRTIS data later today. But first, let's see how near-infrared spectroscopy works for Venus. So it has been observed that actually not all the atmosphere is totally opaque, but there are some spectral windows, so-called spectral windows, where the signal coming from the surface of Venus can be detected. And these windows have been studied by ground-based observation by Madoff and Crisp in 1996. And they have also been studied by flyby observation of Venus from HADAR's mission. Maybe I removed this, sorry, okay. And sorry, I get back. So what it has been studied from flyby observation, the Cassini orbiter, the Cassini mission studied these spectral windows using the Cassini visible and infrared mapping spectrometer, the Galileo mission using the near-infrared mapping spectrometer, and also the solar probe using the Parker Solar Probe Wide Field Imager. And finally, last but not least, the visible and infrared thermal imaging spectrometer on board of the Venus Express mission mapped the near-infrared thermal emission coming from the Venus surface in three spectral windows covering the 1 microspectral region. So what happens is that for Venus, the thermal radiation coming from the surface and the low atmosphere dominates the near-infrared spectra of Venus in the night side. why in the night side? Because during the day side of Venus, we have so much reflected light from the clouds and the atmosphere that we cannot get the signal coming from the surface. But if you observe during the night side, then the surface thermal emission can be detected. And surface thermal emission is directly linked to surface emissivity that can be used to constrain the global surface composition of Venus. However, it needs to be taken into account that the radiation that comes from the surface of Venus is passing through the atmosphere. And during this path, it undergoes through a scattering phenomena in the clouds of Venus. And this scattering makes it difficult to retrieve the signal coming from the surface. And we will see how it is possible to extract from Virtis data the signal coming from the surface, taking into account all these phenomena that happens instead into the atmosphere. But let's talk first a bit about Venus Express. Venus Express is a mission that studied the complex dynamic and chemistry of Venus and the interaction between atmosphere and surface. It has been launched in 2005, and as Lucia said, it studied Venus and the atmosphere and the whole system of Venus between 2006 and 2015, so for several years. And on board of Venus Express, the Virtis spectrometer was the first spectrometer that continuously measured the night side thermal emission of Venus. Virtis is an imaging spectrometer, and it combines 3 different channels. The Virtis M visible channel is a channel that observes Venus in the spectral range between 0.25 and 1 micron. And this is known as the mapping visible channel of the instrument. Virtis M instead is the infrared channel that observes Venus between 1 and 5 micron, and is the map infrared channel. And Virtis H instead is a high resolution spectral channel that it was mainly used for atmospheric studies. Here we will focus on Virtis M infrared channel, because it's the channel that allows to observe the surface of Venus in the 3 small atmospheric windows at 0.2, 1.10, and 1.18 micron. And but how can we retrieve the surface emissivity from Virtis data? So as I was mentioning before, the Virtis data needs to be corrected for atmospheric effect and also for surface temperature. And atmospheric effect includes the scattering of the clouds. So you imagine that you have the radiation coming from a point of the surface. This radiation has to go up to the atmosphere to be detected from our orbiter. And through this path, it gets scattered several times. So in the end, what we see at the top of the atmosphere is just a blurred image of what we have on the surface. And this limits a lot our resolution of what we see on the surface. And also surface temperature can be constrained using radar altimetry. So taking the temperature indication from the radar altimetry and using some models known as radiatory transfer models, it is possible to retrieve emissivity. However, it's not possible to retrieve absolute emissivity, but what we can work on is a relative emissivity map. So we assume what is it, the average emissivity that we have, comparing what we see with lander measurement and with radar measurement. And then we study the anomalies that we observe in the Virtis data compared to this average emissivity. So we talk about high emissivity anomalies and low emissivity anomalies. And what it has been observed studying Virtis data is that there is a relationship between the near-infrared thermal flux and the main morphological units that can be observed on Venus with the Magellan data, with the radar data. For example, in the previous slide, if I go back here, you see Idun Mons is a volcanic structure on the Venus surface, and overlap to the Magellan data here in this image, you have different colors, in different colors reported the Virtis data. And you see in red the areas where you have a high emissivity anomalies, and in blue where you have low emissivity anomalies. And you see how these emissivity data follow the morphological trend, the topographic trend. And you can see also the same here. The map on the top is the a Magellan radar map, while the map on the bottom is the surface emissivity map retrieved from VIRTIS data. And you can see how the emissivity anomalies also here match the topography behavior in the map on the top. But in order to, so we know how to link now emissivity with morphological features, but how can we retrieve mineralogical information, rock composition information from the emissivity data? So what we need is a comparison with laboratory data, but not just with laboratory data. We need emissivity data, laboratory emissivity data at Venus temperature. And also we need a comparison between orbiter data and in situ data, like the one collected from the Venera landers. Let's see what we need exactly in the laboratory to correct interpret the Venus emissivity data. What we need is not reflectance, because what we have when we observe the night side of Venus, that we don't have the sun as a source of light, which is eating our planet. Because when we study reflectance, what we usually have is a source of light that is eating our planet or our material in the laboratory. And what we analyze then is the reflected light. The reflected light in one direction in the case of biconical reflectance, of the reflected light which is integrated in all the direction in case of hemispherical reflectance. But in the case of Venus, since the surface temperature is so hot, what we have is that what we analyze is the light that is emitted from the surface itself. So our source is not the sun, but is Venus itself that shines. And then, so we detect what really come from the hot surface. And what we want to have in the laboratory is exactly the same. We want to eat our samples at Venus temperature, and we want to see what comes out from the sample itself, because we cannot compare directly emissivity with biconical reflectance. And because also it has been observed in the lab that the effect on temperature on the spectral behavior of materials, minerals, and rocks, it is important and it cannot be neglected. So I put here as example some measurement that we perform in the Planetary Spectroscopy Laboratory of DLR in Berlin, where there is an emissivity setup, a chamber where we can actually eat the sample at Venus temperature and measure directly the emissivity. And what has been observed is that there is a 30% emissivity difference between basalts versus granites. And if we see these emissivity differences in the VIRTIS data, or emissivity data from the Venus surface, we are able to say, okay, what we are observing here is the signal coming from a basalt lava flow, for example. And what we are observing here is instead a signal coming from a granitic rock. So what it has been also confirmed through laboratory measurement in emissivity is that the emissivity in the 1 microspectral region, which is the region where we observe Venus, is sensitive to the iron content of minerals. So once again, we have that if we observe region of high emissivity, this might indicate unweathered and recently erupted basalt. As you can see, in fact, here in the plot on the left, you have high emissivity for basalts and basaltic andesite, while you have low emissivity for granitic rocks. So regions of low emissivities are associated mainly with the tesseract terrain that Lucia described to you before, and it might indicate instead felsic composition, and probably they formed during a more clement era during the Venus history. So the other important point, so first important point is comparison with laboratory data. The other important point is comparison with landing site data. So we have the indication of surface composition given by 4 Venus lander mission, Venera 8, Venera 13, Venera 14, and Vega 2. This 4 missions landed in the southern hemisphere of Venus that has been observed by the VIRTIS instrument in the near-infrared spectral range. And okay, it needs to be said that these landing sites are in some regions where the vertex coverage is not super good, but we can correlate quite well the analysis performed by these lenders with the emissivity anomalies observed by vertex. In fact, what we can say for the venerate landing site, this landing site is located in the V43 quadrangle, and according to vertex data, this is the region where we observe an average to low thermal flux. While in the Venera 13, which is located in the Venus 14 quadrangle, this is a region with low thermal flux. Venera 14 landing site is located in a transition between low flux area to high flux area, while for Vega 2 we have an unreliable determined flux through vertex data. But for the compositional data that have been obtained from the lenders, it has been observed that the Venera 8 landing site has a composition that can be related to felsic rocks like the rhyolite, or intermediate composition, or another type of rock which is known as leucitic, and it contains a feldspar. And the same can be said for Venera 13. Also, the elemental analysis that have been performed in this landing site are consistent with this rock. For Venera 14 and Vega 2, it is mainly observed that probably the composition is basaltic composition. So it can be more similar to the mid-ocean rich basalt composition that we have on Earth. Also, it has been possible to correlate the Venera landing site compositional data with the laboratory emissivity data. And it has been observed, for example, in the case of Venera 9 and Venera 10, that the data obtained by the lender match laboratory emissivity data that have been obtained in DLR Berlin, and this data indicates a basaltic composition. So in the end, if we combine laboratory data, ground-based lender data, and the vertex orbital data, we can interpret the Venus surface composition in this limited 1 microspectral region. Here you have a map where you can see the location of the Venera 9 and Venera 10 landing site compared to the landing site of the other landers. So what happened is that discovering that we have these spectral windows that allow us to look at the surface of Venus provide a new technique for further studying the surface of Venus. This is why the next decades of mission to Venus will carry instruments that will be mainly focused on the 1 microspectral region. As the Venus emissivity mapper, which will fly on the next NASA Veritas and Design Vision mission, and Jörn Halbert this afternoon will talk more about this mission and these missions, and the Venus descendant imager that will acquire images of the Venus surface around 1 micron, and Marty Gilmore will talk more about the the Da Vinci mission and the Bendy instrument. So we will see this afternoon more in the hands-on. How can we map the Venus surface using the vertex emissivity data in the 1 micron? And this is all. Thank you.